Hi everyone, my name is Newton, and this will be the second Leetcode practice video. In this video, I will be going over Jump Game 2, which is a continuation of the first Jump Game problem that I solved in my first Leetcode practice video. So let's get into the problem. You are given an array of integers nums, where nums of I represents the maximum length of a jump towards the right from index I. So for example, if you're from nums at I, you can jump to any index I plus j where j is less than nums I or equal to, and I plus j is less than the length of nums. So in other words, you can jump any distance from your current position to the number that you have at that point. So real quick, let's jot down the input and output. The input in this situation is an integer array. And we also want to note that nums of I represent jump distances, or maximum jump distances. Where you can jump anywhere from one space forward to whatever number is at nums at I. And the output is, let's see, the minimum number of jumps to reach the last position in the array. Okay, so we have our input and output, but we do need to write some more information about the context, the constraints, anything that might give us more information about what we can work with for this problem. So scrolling down to constraints, I can see that nums of length will always be at least 1. So nums, like, there will always be at least one position. That tells us that we won't have to deal with the edge case of an empty array. But that does lead us to the edge case of what happens if we only have one position. Well, that's something I'll keep track of in the next step. So let's look at the other constraints. We have 0 is less than or equal to nums at I, and less than or equals to 100. But I think the important thing to note there is that the amount of jump that you will have will always be non-negative. So you're not going to deal with a situation where a jump takes you backwards. And I think another important thing to note here is that this problem notes that you may always assume that there is a valid answer. This is a pretty big difference from the last problem, where you were supposed to return true or false for whether or not you could reach the last point. But for this problem, you can always assume that you can reach the last point. The question is just a matter of figuring out the quickest way to get there. So let's look at the edge cases. The constraints of this problem or the way that this problem is set up, doesn't create much room for many edge cases, which is nice. But because there will be always at least one position, how do we handle exactly one position? Well, if there's one position, we just return 0, because we're already at the final step. So let's start working out explaining how this problem is going to work and figuring out how we're going to solve it. So let's look at the examples. We have 2, 4, 1, 1, 1, 1. And here's what the answer is for this problem. The output is 2, and that's because we went from the first jump. From the first jump, we could either go from 2 to, we could either move 1 space forward and landed on a on a 4, or we can move 2 spaces forward and land on a 1. We chose the 4 in this scenario because 4 is much more has a much gives a lot more space than 1. And once we go to 4, we then see that we can reach the final position from this point. And what we do is we then jump 4 spaces. We're currently at position 1, so 1 plus 4 spaces means we jump to the last index. Okay. These notes may be a little confusing to follow, but I think we get the point with like picking the best jump and using that to minimize the number of jumps we need to reach the last position. So let's look at a few different algorithms we can consider for solving this problem. For one, I can mention the brute force approach, which is to go through every possible jump pattern, or every possible jump decision that you can make, and just return the minimum, the path that took the minimum number of jumps. This is the brute force approach, but of course it is extremely inefficient. So for efficiency, we'd like to pick something else. Another thing we can look at for solving this problem is the dynamic programming solution. So it's something that I mentioned quite a bit. It's something that I alluded to with how I went through this example, but this is how that solution goes. You start off at one position, and then you compare all the possible values of jumps you can make from that position. So from the initial position, we compare jumping forward 1 space with jumping forward 2 spaces, and we see which solution takes us forward farther. In this case, jumping forward 1 space brought you to a 4, which was the better solution. However, the dynamic programming solution is also less efficient than what we could need. Just for reference, it is O of n squared, and that is because we're potentially comparing we're comparing like potentially the same each time we make a jump, we have to compare every single possibility of jump and then choose the best one, and then repeat that process from there. Choosing the best possibility of jump could potentially be the entire list. Or I guess with these constraints, choosing the best possibility, the best jump, could potentially take 100 steps. And that is the loop that we would have to run every time that we make one jump to the next. And because of that, we're pretty much defining a nested loop type of structure, where the outer loop, you make every jump. You make the jumps. And then we have an inner loop where you compare each possible jump. So we're going to have two loops if we attempt this dynamic programming solution, and that will cause us to have an O of n squared time complexity. We don't need to use space for this problem. We don't need any more than a constant space. But, however, we can come up with a more efficient solution. Now, I need to admit, this is not my first time attempting this problem. The first time I attempted this problem, I attempted the dynamic programming solution. I then ran into a time constraint, and then I was not able to pass this question. I then attempted a version of a greedy solution where I would constantly take the next biggest jump that I could find. But of course, that wasn't a greedy solution. In its own way, it was almost a brute force solution, and it did not pass all of the test cases. But now, after reviewing the solution code and giving myself some time to think about it and reflect on it, and then realize how I should have been thinking about this problem, I'm coming back to attempt this problem again. So here's the greedy solution. That is O of n in time complexity and O of 1 in space. This is the most efficient solution that we can have for this problem. So first, let's explain how this solution works. So instead of let's go back to our dynamic programming solution. We have an outer loop where we make each jump, and we have an inner loop where we compare each possible jump. But what this greedy solution does is it looks at this solution and it asks the question, do we need to compare every possible jump? When we can instead zoom out and look at the bigger picture. What we do here, and let me work this out on the example. We start off we start off by looking at a range of possibilities. We make the outer loop jumps, looking at like every possible jump that we can make at the same time, essentially. So let's start off at the initial position here. And from 2, we can jump to either 4 or 1. Every possible, let's call this group jump 1. Every possible jump in this group, or every position in this group, can be accessed by making one jump from the initial position. So that's why we're going to call this group jump 1. So here's what we do. We go from 0 to the jump 1 group. Now, how do we know where we can move after this group? Well, we can either jump 4 spaces from the first position or 1 space from the next position. And if we take the 4, we can jump either 1, 2, 3, or 4 spaces. And if we take the 1, we can only jump 1 space. So both of these possibilities give us a range that we can reach, which is from this position, this one, all the way to the end. Let's call that group jump 2. In this case, we're not spending time to look at what's the best solution between 4 and 1. We're just looking at what's the maximum solution in this whole field. And then we're creating another field. And with that type of approach, we can solve this problem with only a single iteration. So let's start trying to implement this. We're not looking at a specific best jump. We're instead looking at ranges of jumps. So how do we implement something like this? Well, first of all, how do we know that to create these boundaries, jump 1 and jump 2? We can try using a two-pointer approach to implement that. Maybe something in between a two pointers or sliding window type of thinking, but we can have one pointer denote the left boundary of the jump, and another variable keeping track of the right boundary of that jump group. And then each time we make a jump, we're just iterating both of these variables to where the next jump group is. So when we make the first jump from 0 to jump 1, left becomes 1 and right becomes 2. Once we make the second jump from jump 1 group to group 2, left becomes 3 because it's one space after the current right, and right becomes 5, which is the maximum space that we can get, the maximum position that we can achieve from jump 1. So where do we end? Well, we want to end when the right boundary has reached the end. That would tell us that we have reached a winning solution in that number of jumps. So perhaps we should also use a variable to keep track of this. So while right is less than length of nums minus 1, okay, we want to make a jump. And how do we know that we want to make a jump? That's if let's see. Okay, here's how we can do that. We want to loop through each variable between left and right. Okay, so we want to loop through each position between left and right, and we want to at least loop once, so that's where the +1 comes from. And what we want to do is keep track of the farthest area we can jump to from this position, because that will be what helps us decide the next jump boundary. So let's see. Oh, sorry, I should create this variable outside of this loop. Yes. So the farthest position we can make is simply I, the position we're making the jump from, to nums at I. And of course we don't want to just set farthest to this value. We want to make sure it's the maximum. And once we figure out what the farthest distance we can make is with that jump, we can decide what the next jump is. So so really this step can be called decide farthest jump. And then this part can be called make the jump. So what happens when we make a jump? Left becomes right plus 1. It's the jump after the right position. Right becomes the farthest value that we could jump to. Yes, it does. Okay. So that helps us define where the two jumps are. But every time we make a jump here, we need to increase the number of jumps by 1. And then once we exit this loop, once we have reached this right is less than, we've broken this condition, we can finally return the number of jumps. So now let's try testing this solution. Okay, as we can see, we were able to pass both of our test cases. And if we try submitting it, we hit the wrong answer. Okay, so let me look into this solution and figure out how to debug it. So what happened here? Okay, so it made a jump from 1 to 2, and then made a jump from 2 to to this position, and then it made another jump. So let's take a look at this. Let's use this test case, and let's run it through this code manually. So first, left, right, and num jumps are all set to 1, or set to 0. We decide the farthest jump by looking at the range between left and right minus 1, which in this case, it just picks the farthest, which is, in this case, 1. So left becomes 1, right also becomes 1, and the number of jumps now becomes 1. We then move to the second loop. We decide the farthest jump. Farthest becomes equal to 0. And from this point, we can see that for I in range, yeah, we're only looking at one position here, but I see. I think what I'm doing here is I'm calculating the farthest, like calculating the, I think I'm on the right track, but I'm missing what's exactly causing this error to occur. Farthest is set to 2, and then we make the jump from here. So the left value now becomes 0, and the right now becomes 1 plus 2 to become 3, index 3, and number of jumps is increased by 1. What should have happened in the third loop is that we break out of the while loop because right is now equal to length of numbers minus 1. But it did not do that, and I suspect that it may have something to do with how we're calculating the farthest value. So let me debug this. I want to take a look at where I'm jumping from, as well as the number, just to see what space I get, and then I want to print out the farthest value. And let's try this again. Okay. Okay, that is very odd. So we print out I and nums at I. Ah, I see. Okay, so what's happening here is we're not keeping track of the current position. We're only keeping track of we're always iterating from 0 to this number instead of, in my mind, we were iterating from between left and right. So I think I need to rewrite it like this. That was able to pass this case, and let's look at the, yep. So what I went through in my manual example did happen here. The first jump was a choice, was simply position 0, jump 1. But the second, we did take the 2, and we jumped accordingly. So let's try this again. Okay, so there is another test case that did not make the cut here. And what's happening now? Okay, I can see that what it's trying to do here is it sees that the position is 1, and the farthest possible jump is 1, and then it's calculating the farthest jump as 2, when in reality that's actually the farthest position you can make from that jump. So I think instead of tracking the farthest position, I should just track the farthest jump itself. So I removed I, and let's rerun this script. And now with a bit of debugging, I was able to complete this problem. As you can see, I have a 1-day streak, but yes, removing the print statements, we can resubmit this, and we can see that our solution is optimal in runtime and memory. All right. Oh, I'm a bit sick today, but yes, that will be it for today's Leetcode practice problem. I did struggle a little bit, but I was able to at least get through it, and I will be posting this video regardless. But thank you all for watching, and I'll see you in the next one.